All right, hello everyone. Thanks for coming. I'm going to be talking to you about how Citus data scales out Postgres and how it does it on AWS. Is that the forward button? So my name is Will Lineweber. You can get in touch with me, Lineweber on Twitter. Our website is Citus Data. And so just to go over the overview of what's going to happen in this talk, there's two major parts of the talk. First is what Citus is, how it works as an extension on Postgres. And then the second part is how we've built a cloud service for it. And you know, those sorts of things. And so the first part, Citus is an extension on top of Postgres. And we're going to get into our talk about how that enables you to scale out Postgres, both in terms of disk storage, but also the memory usage, so you can control how much is cached in RAM, and also if you need to scale out your compute. And so using Citus, you can scale out all those different components of your database. And then the second half is the orchestration part of how we built a cloud service on Amazon. And even if you're not going to be using our cloud service, hopefully there's some tips and tricks that we've learned over the years to, that you can use in your own developments of Postgres or other sorts of cloud services. And we're going to go over things that worked surprisingly well, disaster recovery, a little bit on microservice monitoring, and those sorts of things. Just curious here, who uses Postgres today? Okay, that's nice. Good. You all have good choices and taste. Secondly, just curious, has anyone tried Citus before? Okay, a couple people, that's nice. All right. Yeah, this isn't. Okay, so to get to the second part, to understand the design of the service, you first have to know a little bit about how Citus works. So the first most important thing is earlier this year, we open sourced Citus and made it just an extension on top of Postgres. Rather than it being a fork of Postgres where it would be a modification and that would make it harder to stay up to date with advances as Postgres advances, currently it's just an extension on top. And that way it's still a little bit of work on our end, but it's pretty easy for us to, when a new version of Postgres comes out, like when 9.6 came out, and next when Postgres 10 comes out, to port our thing forward so the extension continues to work. And the upside is people who use Citus can take advantage of new Postgres features almost on day one. And for those of you, and many of you were using Postgres, you know that every year Postgres, maybe there's not a huge release every year, but there's always something nice that you want to be taking advantage of. And because we're an extension, it's very easy for us to continue to support those things. So what Citus does is it turns Postgres into a distributed database. Many apps, eventually outgrow single node Postgres. Either, maybe, data starts becoming, coming in at an increasing rate, or, very frequently people no longer start deleting their data. I gave a talk once on some strategies to mitigate Postgres growth, to try to stay inside single node Postgres. By actually deleting your old data, and I really wanted people to do that, but it turns out organizations, they just have an addiction to storing as much data as they possibly can, and just end up never deleting anything. And now that I'm at Citus, I'm like, that's fine. You should keep all your data forever and use a nice distributed Postgres. But even outside of that, there is plenty of reasons for legitimate reasons why you have a lot of data and you need. And it's just too much for single node Postgres. Usually people start hitting limits on the amount of RAM that you can have in one machine. I know announced recently over the last couple of months and today more and more bigger Amazon machines with more and more RAM, but still there's a limit to how big that can get. And then also Postgres itself, the 9.6 I believe has some advantages with parallel query, doing sequential scans in parallel, but really like aggregates and stuff in parallel, like being able to scale out your CPU. I've seen some, going on some customers' calls, I've seen using equivalent amount of spend on single node Postgres to a small cluster of Citus, up to like 100, 150x improvements because they were CPU bound. And Postgres by default just has one backend, and you're limited mostly, more or less, with some caveats, to one processor working on the data. And so Citus takes care of sharding the data to many nodes. It takes care of routing queries to the appropriate node, parallelizing the queries to do all the work in parallel. And the exciting thing is the worker nodes are nothing special. They're just Postgres instances. And what I mean by that, in the terminology that we tend to use a lot, we have worker 0, worker 1, so on and so forth. And on these workers, there's shards of data. And so we can have, your one table could be split into maybe, let's say, 64, 128 shards. Some of those will be on the first worker, some of them will be on the next worker, and so on. And what's really going on is these are just servers and tables. So each one of these is a normal Postgres server that if you're operating it yourself, it operates in much the same way, similar backup, disaster recovery sorts of things. And the actual shards just show up as tables. And just to drive that home a little bit, on the coordinator node here that takes care of running some queries, I'm listing, using \DNP-SQL to list what tables I have. And this is actually a production database that I use myself. And we'll get into some of what these tables are later. I just have two little tables here. But when you go to one of the worker nodes and run it, you can see here now there's the same tables, but with their shard number placed on them. And if you do connect to this, you can actually just look at it, and it's just the normal table, but split up into these little pieces. So when a write comes in, like an insert, update, delete, we look at how it's sharded. So when you make a table, you say, I want this table to be sharded by this column. And so when the query comes in to do a write, we know where that's going to end up. We hash that value. We know which shard and therefore which server to go to. And we go and do that write operation. And the way we do the hashing, there's a little, the catalog table. And you can see here that the first shard takes, negative, 2 billion, whatever, to the next version, so on and so forth. And those are that's how we know where the shard ends up. And that's how writes go no matter what. Now, there's two sorts of ways that we see people using Citus most frequently. One is like a real-time SQL on event data, and the other is sort of a multi-tenant model. And I'm going to get into both of these. And so the first one, the multi-tenant model, this is if it's the system of record for your like multi-tenant SaaS app. Let's say you have an application that you have individual customers. They each get their own silo of data, but it's the same set of tables for each of your customers. And for example, Salesforce, other sorts of reporting, sort of apps where if you were going to shard this yourself in the application layer, what you would do is have a number of Postgreses, maybe using, I've seen this a lot, unfortunately, using the Postgres' schemas to do the sharding, which if anyone's doing that right now, be aware that like pgdump starts to fail over after you get a certain number of tenants, and that can be, I saw one where just planning queries took minutes because of all the just schema objects, and it was a nightmare. So anyway, but I see, that's an approach that, so every single customer has their own sets of tables. And if you use that on Citus, instead of having to put that logic in your application, you can have the database take care of doing the logic of sharding out each one of these tenants for you. And the nice thing about this sort of multi-tenant approach is it's easy to do migrations. It's easy to migrate do migrations of your source, when you're adding columns and such, because you only have to do it in one spot. You don't have to track down each of your columns, each of your tables across all your databases. You can do the DDL in one spot. That works very nicely. It's also simple to go, if you're already doing this on a single Postgres now, you can migrate into multi-node Citus, fairly straightforward. You don't really have to rewrite much of your application. You get I think pretty much all Postgres just works in this model. It's easy to maintain. High availability works the same way as you would use in your Postgres. Backups, you can use pgdumps, you can use wall shipping, that all works fine. And it's easy to scale both vertically by making the worker nodes individually larger instances, or you can add new nodes to the cluster as you need more, as your demands increase. And just to get into how this works, it's important that all of the tables have the same shard key. And so if you had customer ID or tenant ID or organization ID, those are the common ones I see. Each table, you normalize that out, so each table has that reference. And then as long as the queries all go in, reference that same column when you're doing the sharding, everything works just nice. And just to illustrate this a little bit more, let's say we're using org ID as our key. The query comes in and it says, whatever, and then where org ID equals 3. We know how to shard that. We know how to, what shard it goes to, what server it goes to. The query gets routed there. It executes, and you get your data there. And this is, pretty much, nothing's magical is going on here. This is like exactly as you would do it yourself were you to push the sharding logic into your own application. The other model is pretty exciting, the sort of parallel kind of NoSQL-ish model. And this, you can do normal SQL pretty much on trillions of events for like real-time analytics. Sort of the advantages here is that you still get to use Postgres. You get to use your Postgres drivers. It's more familiar than having to go to a complete rewrite system like Cassandra or something else. You get to keep more of your experience in-house. Lower cost, you can use your existing team skills. Also for orchestrating and managing, it still feels the same as Postgres. And you get to take advantage of extensible features. For example, when JSONB landed a release or two ago, that makes it a great store for being able to have indexes on sort of semi-relational data and sort of mix the two, having real columns and sort of like an amorphous extra data, and be able to do computation on both. And the other thing that's nice, just going back to the cost thing, because it is Postgres, you can spill to disk. You can have, some solutions in this thing are in memory only, and that can get very expensive as you have to keep adding new machines to because RAM is very, very expensive. Because this is Postgres, it operates the same way. You can have, just a portion of your data set in RAM and the rest spilling to disk. And the way this works is when the query comes in, now we're sharding on something different. Maybe we're sharding just on a UUID to distribute the data randomly. Maybe we're sharding on, timestamp, or depending on depending on your application, choosing the right shard key in this is important, and it's sort of application specific. But when the query comes in, because you're not saying that same shard key, what happens is the query gets parallelized and it hits every single one of your servers. And in this way, the computation happens in parallel across not only all the servers in your cluster, but all the CPU cores in your cluster. And so you can put your entire cluster to work doing aggregations that can be pushed down, and then the data that the stuff that can't be pushed down gets brought back up to one of the nodes, and further aggregations done there, and then it returns back. One of the things, though, because this is splitting off the work and doing stuff in parallel, now you start getting into a couple trade-offs. Some complicated CTs can't work, but it's a lot of SQL, but it's not all SQL. Whereas before in the other model, because it was going to a single node, we're able to do full SQL coverage. This, because we're splitting things apart, certain aggregations that rely on accessing all the data at one time, those are harder to do. And we're increasing our SQL coverage over time, but right now this is where you might run into a couple stumbling blocks. And if any of you do are using Citus and you run into something when you're doing this, we have a very active Slack channel and people where we can, help you, walk you through this. Because this is maybe, of all the places where there might be a stumbling block, this is maybe one of them. But it's not so bad. And because of this, I mentioned before, this is one of the customers where we saw like 100, 200x improvement because their workload was CPU bound. Being able to push it out and hit all of the nodes, that's how you get some pretty incredible performance increases. And one of the more recent things that we announced back in September is Citus MX, and I'm pretty excited about this. All the previous ones, when you would issue a query, it would go to one coordinator node, and that would do the work of aggregating the data. Citus MX now, you can, when you connect to it, you get assigned to any one of the nodes in your cluster, and it sort of is, sort of a no master kind of approach. And with this approach, the write scaling goes really huge. And we have an example here that I'm going to show. I was a little bit too nervous to do the example live, so I had one of my colleagues recorded a demo. I didn't want to tempt the Wi-Fi demo gods here. But just an overview of how it works. There's still a coordinator node, but all it's used for is when you're doing DDL. So that's create table, alter table, and that's just to keep everything consistent when you're doing those very infrequent but very important updates to your schema. The rest of it, the inserts, updates, deletes, and queries, they go to a round-robin DNS to go randomly to one of the worker nodes. And so this is how all of the writes can be happening in parallel, not bottlenecked on a single thing. And so this is I think, about 4-minute example of using Citus Cloud to provision one of these Citus MX and going through the YCSB, I think, the Yahoo Cloud benchmark to do that. And I think if I do that.
In this demo, we will set up a Citus MX formation using the Citus Cloud console. I will use 4 nodes in high availability mode, meaning each node has a hot standby, which automatically takes over in case of failure. Once my formation is ready, I will see the dashboard where I can monitor and change my formation, and I will find URLs to connect directly to the Postgres nodes. I can get started with Citus by connecting to the coordinator. The coordinator is a small additional Postgres node, which I only use for administrative commands. Citus is an extension to Postgres, which adds the ability to distribute tables across many servers. I can create a distributed table by first creating a Postgres table, and then specifying the distribution column and creating a number of shards. Each shard will contain a different set of device IDs. After creating a distributed table, I can start using the data URL, which connects me to a random data node. Every data node contains a different set of numbered shards, as well as the distributed table. Writes to the distributed table are routed to a particular shard based on the device ID. If I then get connected to a different node, I will see the same distributed table with all preceding writes in a consistent manner. Now let's add some more data to our distributed table. This tool starts a number of threads which send individual inserts to the database via the data URL, getting a throughput of around 15,000 per second. If I want higher throughput, I can easily scale out my cluster by adding more nodes in the Citus Cloud console. After a while, the new nodes will come online without interruption, and I can see my throughput increase and my latency drop because my queries are now being routed via 8 nodes instead of 4. However, my data is still on the original 4 nodes. To solve this, I can run the shard rebalancer, which automatically moves shards between the data nodes one by one. While the shard rebalancer is running, queries on the distributed table can continue as normal, except writes on the shard that is currently being moved will experience higher latency. Once the shard rebalancer is done, the data is redistributed, and I can see my throughput increase to 30,000 per second, twice what we had originally. While my inserts are ongoing, I can still do fast selects, such as this query for a particular device which goes to a single shard. or disk query across all devices, which Citus parallelizes across the cluster. You might be wondering, how fast can Citus really go? So I set up another formation with 32 bigger nodes, on which I will run the YCSB benchmark. YCSB is a benchmark for testing query throughput, which reads and writes on a particular key. I used the YCSB Java tool, which connects to Postgres through the JDBC driver, and configured it to insert 10 million rows of 100 bytes each. To run the full benchmark, I set up 33 driver nodes, one for each database node. To run the YCSB command on each of them, I used the PSSH tool, which runs SSH commands in parallel. After a while, I can see the results coming in, and each node performed around 16,000 inserts per second, which adds up to over 500,000 inserts per second. And these are consistent, durable writes using the Citus Cloud production settings. If you need even higher throughput, you can use the copy command to append a raw data file directly to the distributed table. We put a file with 10 million rows on each of the driver nodes and loaded it using copy. The whole process of loading 320 million rows took only 45 seconds, which is 7 million rows per second. If you're interested in using Citus MX,
so that's, the copy is a little bit cheating because it is just bulk loading. It's not doing it, but it is, I don't like to advertise the number too much because it's just, because it's, it's only if you do have data to bulk load, but the random inserts of the Yahoo benchmark is very nice because it's more accurately simulates what a production load might be. Of course, that's hard to do in a benchmark. It's hard to do real production use into a synthetic benchmark. But as far as benchmark goes, I like the Yahoo one a lot because it is more random writes in different locations. And the bulk loading, that can go so fast because Postgres copy is very fast, and we can route that to the right node, and then Postgres copy just pretty much just splats the tuples straight to disk. And so that's limited mostly on your disk throughput. And so you sort of have two choices with Citus. You can run it yourself. It's open source. You can go take it, play with it today, and there's nothing wrong with running it yourself. But there is a little bit more effort into keeping a cluster of Postgres machines happy and healthy and running than it is to just one Postgres and its maybe a couple replicas. And so because of that, I joined Citus a little while ago to help build their cloud service. And there are some trade-offs to not running yourself, and there is some benefits to not running yourself. One of the benefits is that as sort of a centralized point, we get to see the failure modes of many different customers and sort of take that expertise and put that across and help everyone out. And we see more failures than or weird edge cases dealing with Amazon than you would yourself running just an application for your one company. The downside, though, of course, is it is a loss of control. If you're running it yourself, you have full control of everything, but you do also have all of the blame. And so those are sort of the two trade-offs. I do have to get a little bit into the origins. Many of the original decisions that went into this actually started 5-6 years ago with my former team, Heroku Postgres. I see some of my former colleagues here. Thank you very much for coming. And so, we were able to leverage, many of the decisions and learnings about dealing with a cloud service on Amazon, having, come through and done this, sort of, this is maybe, it's not really, but it's maybe like the 6th year of running databases on Amazon. And I can't overstate like the confidence and that experience gave us. And so, the way that we're doing this, just to set the stage a little bit, we're using a Ruby thing called SINATRA, which is a small API framework to do the orchestration. And one of the things, I don't know, does anyone here use the SQL library for Ruby? Yeah, like if you are using Ruby, SQL is one of the best run projects that I've ever come across. It's one guy, Jeremy Evans, mainly coordinating the project. And if you go to github.com/, Jeremy Evans/SQL. If you go there and look at the issues right now, there's probably 0 issues. And that's not because people aren't reporting it. That's because he closes the issues almost immediately. It's like, and there's the other thing that I really love about SQL is there's one release every month, and it's just the accumulation of some small changes. It's not, some other software projects where, every once in a while there's a big release and you have to do a lot of work to get on top of it and, fix things. This, sort of incremental changes has been, it's a joy to use. So I try to tell people about it as much as I can because it's a great, little known project. Some people ask me, Will, why are you doing, something in Ruby? Isn't it slow? Isn't it, this and that? But the biggest reason, the hands down the biggest reason that I used Ruby again for this project was the interactive console. Being able to, in a firefighting situation, maybe, something is wrong with these 10 servers. Maybe, servers on this particular AMI have some sort of problem. Just any sort of situation. Being able to open an interactive console in production, grab the servers that I need to fix, fire off commands, is just, such a huge performance increase rather, just on my time, rather than having to, muck around with the CLI tool or, have to make API calls or whatever. Having the tool that I operate the service with be the same concepts, the same programming models as the code itself is just removes an impedance mismatch that would be there were there not a nice interactive console. The other big thing that carried over an idea is having mostly immutable servers. We always prefer to throw away a server entirely rather than go in and muck about with the configuration or whatever. Now, this, I say mostly, sometimes if there's a very important, very time-sensitive security improvement, let's say SSL. I don't know if that ever has any security things, but sometimes it does. That is easy to go in right away and just patch that. But if it's something, less time-sensitive, we always prefer to make a new AMI, spin up a replica of the server that we're going to take down, and then do a controlled switch. And that way, we know, there's not, servers don't get weird, configurations because they got monkeyed with a little bit. Things are pretty standard, pretty, non-surprising. And the other nice thing about the servers being mostly immutable is that if the main monitoring orchestration app goes down, the databases aren't dependent on that. They live on. And the way we do this is by having outside-in SSH&PSQL checks. And so rather than have an agent on the box, spitting out, metrics and something that we'd have to go and update as we wanted to do new checks, all we have to do is update the central monitoring application, and it starts doing new checks, new health checks, new metrics gathering, and so on. And this is how there's no the server itself doesn't need to know that it's being monitored. It doesn't need to be sending stuff. We just connect, do some checks. And the other nice thing is because we're doing these connections frequently, we can sort of know if there's maybe a network interruption. Rather than if there was a monitoring agent on the box sending metrics out, we might not be able to notice that there was some sort of networking problem. I do want to go on a little bit of a small, I don't want to use the word rant, but something like that on microservices. So essentially as things grow, we need an approach to breaking up the code and growing the service. I'm sure many of you are familiar already with Conway's law, but just to reiterate, organizations with design systems are constrained to produce designs which are copies of the communication structures of the organization. And when I first heard about this, I don't know how long ago, I thought, this is something to be avoided. The system should be designed as the system should be, and just because there's people involved like that, we shouldn't. That's unfortunate that we have to. This is something that we should fight against. But now I think that it's maybe just unavoidable, and just kind of embrace that it's going to happen and keep that in mind when developing your teams, when splitting out teams, rather than try and fight it from the engineering side. So the upsides of microservices, of course, people go on and on about that for years now, 2 years maybe. The downsides, though, is you can no longer look in a single place, single point of truth. Now you have to do API calls and to figure out what's going on. And while each individual app might be simpler, all that complexity is pushed into the communication channels between the apps, which is much orders of magnitude harder to debug and reason about. And so when building this, I wanted to keep it as few services as possible, but it's still we still needed sort of two different services that made sense to do it that way. One of them is the external UI that you saw in the demo video, that web page. That thing takes care of user-facing things. And the other one is the internal control plane, which handles managing the fleet and so on. To go into detail about the two things, the console, we also do billing. We show metrics. And the reason this makes sense as a separate thing is because this doesn't get interacted with that often. It's only ever responding to people going in and clicking around. There's not, it's not an automated service that computers are talking to. It's just a human interaction thing. And for this one, we do use Rails, but we swapped out Active Record for SQL just because I already went on my how much I love it, but it was great. And the control plane, this is what does the server provisioning. It does the monitoring. It does healing of disaster recovery. It's really the sort of the brains behind the cloud service. And this one uses SINATRA and SQL, and that's going to be the focus for the rest of the remainder of the talk. The commonalities are Ruby and SQL, which I mentioned. And before we go further, I need to introduce some of the concepts that I'm going to be talking about how we model running a service on Amazon. One is the formation and server. So a formation is the entire Citus cluster. How it's all the primary machines that are doing the work, all of their replicas that are there for disaster recovery. A server is an AWS instance. And we started with just this. We've made it a little bit more complicated because servers get replaced over time, but they have the same role. Worker one is always worker one, even if the Amazon server behind it changes due to failover. And just before I maybe say something, is anyone here from AWS? Okay, so as you know, Amazon can be a hostile place to run apps, especially databases. And so because of this, over time, we've developed different ways to handle failover, handle replication, and durability. The main tool that we use to do that is a tool called WAL-E. And data protection, I see this as the most important thing. Higher than availability. If a customer loses their data, perhaps their entire business could be down. If it's just downtime, you want to avoid downtime as much as possible, but losing or corrupting data is often much, much worse. And so what WAL-E does is it takes PostgreS's archive command, and every 16 megabytes or 1 minute, which is the default Postgres configuration, you can tune that a little bit. It takes that WAL file and sends it off to S3. And so even if you're not using my service here, if you are running Postgres on AWS, please use WAL-E. I can't count the number of times that having the WAL off the machine has saved us. And so the other thing it does is that once a day you can script it to take a base backup, which is the entire archive of the database, and then do the WAL for that. And the other thing that this allows you to do is point-in-time recovery. And so a timeline of a database, each one of these diamonds is the base backup. So that happens once a day. And then in between here, you have the incremental WAL segments. And so what you can do is you can set up, easily if you have this set up, you can bring on read replicas by taking down the last base backup and having it replay the WAL off of S3 until it gets caught up enough to switch into streaming replication. And then you have very fast replica ready to go for failover or what have you. And these replicas, of course, are read-only because that's how PostgreS's streaming replication works. And then if we do have to do recovery for some reason, we promote one of those standbys to be the new primary for its role. If it's worker 1, worker 2, it becomes the new primary. It starts generating the WAL segments, and then we throw away the old one. And so that if that replica exists, we can do that very quickly. But even if it doesn't exist and the server's just down, because everything is off the machine on S3, we don't necessarily need the primary to still be running to create a replacement. And so there's lots of reasons to cycle machines. One is unavoidable, unexpected downtime. The other one is if we want to experiment with new disk layouts. You do scheduled maintenances from AWS saying that since this is about to be retired, we can use this to quickly switch over to a standby rather than go through the restart. And because both disaster recovery and sort of scheduled known maintenances are using the same mechanism, the disaster recovery gets battle tested more frequently than an unexpected outage. The other thing that model that has worked very well is sort of doing video game developments. One of my first managers spent some time in the video game field and applied that to Amazon. I put this slide once in a talk I gave in Moscow, and I thought they would like it because it was Tetris and it was from Russia, but they didn't laugh. So, and so there's 2 phases to this video game development. One is a feel or an observation of what the world is. So this is the health checks that go in. We look at the environment to see what is true, and then the second phase is a tick, and we operate on those observations we just saw. And what we do then is we perhaps change state, or we stay in the same state. So this is a simplification of sort of how we reason about Amazon instances. The first stage is creating, and that's when we are provisioning the machine. We're waiting for it to come up. We're waiting for the network interfaces to attach, so on and so forth. And then it goes into the available state. And once it's here, this is it'll stay here for a majority of the time. And then if we notice that something went wrong, maybe we weren't able to connect to Postgres, we weren't able to SSH in, we'll go to an uncertain state. Rather than just immediately call the machine offline and go through failover, perhaps it's just some sort of short network blip. And so we wait in the uncertain state for a minute or two just to be sure that we're not going to go through disaster recovery when it's not necessary. And if everything goes back, then we'll pop it back into available. Otherwise, we'll go into the unavailable state and start doing disaster recovery. We'll try to restart the machine. We'll at the same time bring up read replicas and so on and so forth. And the key here is that we're always trying to converge to that available state. No matter what happens, we want to get back to that state. And one of the things that is nice, there was earlier this year, I forget exactly when, there was some sort of Elastic IP outage in US East, or I forget the details, but what you needed to do was deassociate the EIP and reattach it. And rather than have to write a new script and go through and do that for all instances, we were able to just deassociate all of the IPs and trust that the state machine would do the right thing and converge and do the reattachment. And that's a very nice way to, a very nice thing to rely on. And it's, the other thing is, one of the last parts is these job queues. And that's what's doing all of the work to do the health checks and so on. And spent some time looking at a couple different couple different queuing services and so on. But SIDEKIQ is a Ruby one that, and a couple other languages that uses Redis for the store, and it's very, very fast, very performant. And the first sort of iteration on this, we relied on jobs re-enqueuing themselves. So a server would do the server work to check and then re-enqueue itself back into the queue. and that worked pretty well, but then sometimes when there'd be a big exception, a big, big problem, they would fall out and it wouldn't re-enqueue itself. And and then spend some time trying to go through the queue and see what was missing and re-add those, but that eventually gets slow as the number of servers you monitor increase. And so the approach we use now is every 5-10 seconds, we look at the size of the queue, and if it's starting to get small, then we re-enqueue the work for looking at all the servers again and again. And so that way, the queue never runs empty, but it's never, it doesn't overflow. It's not super full. The other thing that's interesting is, so we have all these servers doing all these checks, potentially making very important decisions to kill a server because we want to make sure it's down before we bring up the replica. And so we want to make sure that there's no races, that we're not, don't run into any concurrency problems. And the approach that my colleague Dan Frino settled on was this semaphore approach. And so, for example, this example, we're adding a node to a formation to increase the total compute size of the Citus cluster. And so when we're going to add it, so we need to add a server for its placement. And then for each of the servers, the existing servers, we need to go in and reconfigure them so they know the existence of this new node in the cluster. But we don't want to, accidentally, if you press the button to add the node twice, we want to make sure that we reconfigure correctly twice, 2 times. And if we didn't have this sort of semaphore thing in, it would be easy to do it once and say we're done, and then miss out on the second one. And then on the other hand, we look to see if the semaphore is positive. If it is, that means we do have some work to do, and we swap the state into configuring. And then in the thing on the right here, when we're doing the configuration, we decrement it once, do the work, and that way, when someone pressed the add server button twice, we know we're still going to need to do this work the second time for the second server. That is a very brief thing. If that sort of thing excites you about using this to orchestrate your servers on Amazon, this blog post goes into very, very in-depth detail. It's a very long blog post. It took me a long time to read. My colleague wrote it. And so the last sort of thing is how we do metrics collection, and also this gives an example of how to use Citus if you're going to use it yourself. And so customer visible metrics, if you go into the dashboard, you can see some metrics that we're using to see the health of your own service. And the way that this one is stored, you saw the CW metrics table a little bit earlier, and this is a sample row from what it looks like. The CW is for CloudWatch. We're just taking CloudWatch metrics and storing them in our own database so we can do our own manipulations, our own investigations on the CloudWatch data. And so we have a server ID, and this is just a UUID to randomly distribute out across, have the data be distributed across the Citus cluster. We have the AWS ID. This is the instance ID you know and love. And then we have the metrics name, the timestamp of when that metric was taken, and then the CloudWatch information. And the index we have on here is a compound index of server ID, the timestamp, the AWS ID, and the name. And the reason it's the primary key is so wide, rather than just being one column, is this ensures that the tool I wrote to go and take CloudWatch data and dump it into our Citus cluster, if it ever gets out of sync and starts grabbing the same data twice, because the primary key includes the metrics name and the AWS ID and the timestamp and everything, it prevents you'll get a primary key violation, and it won't insert duplicate data. And also, when we do queries on it, usually we do all the way up to the Amazon ID, and then we can, that query, that index is pushed down to each one of the nodes, and so the index we can take advantage of it in parallel. The other exciting metrics thing is admin metrics only. So this is when I log into the administration plane, this is what I see. And originally, I was using an application level exception tracker to store both exceptions that were unexpected, but also these sort of expected exceptions. One of them like being a timeout error. So this is as we're connecting to a server, but it's not yet quite up, SSH will timeout. Or if we're connected currently to Postgres and then it dies in the middle, that might be the database connection error. Connection refused, so on. There's a handful of these exceptions because we're doing these constant health checks that we sort of expect to see. And I was putting them in the exception tracker with the exceptions that I actually want to know about and do a code fix because they're actual bugs. And having those two sorts of things in the same place was not ideal. And being able to graph them like this, though, we can see, here on that Friday, you see that on the first metric there, something went wrong there. Nothing is catastrophically wrong, otherwise we'd be getting paged. But there's obvious that some sort of change went in Friday, probably right before someone went home for the weekend. And something is going wrong, but don't quite know what. And so by storing these sorts of exceptions in our own internal Citus cluster, we can sort of, when we notice that the pattern has changed, we can go and investigate and see what's wrong. And all this table is a random ID, UUID, the name of the exception, the time, and then a JSON B column. And so we can store any sort of data we want in there. And so this is helpful. Like we can store part of the backtrace. We can store maybe what server was being looked at the time. And those graphs that we did there, this is a very simple query to do select count star, the name, truncated down to the hour, and then just look at the last week. And because we have an index on the created at there, we have an index on that, being able to just slice out the last week of data from our ever-growing data set, that index can be used just like any other Postgres index, and it's a very fast query. So I do want to end with one little story of a misadventure that we ran into. When we started, we looked at ZFS on Linux, even though it's better on BSD, but like the ZFS on Linux, it's been around for a little while. Like let's give this a shot. And the initial results that we saw were very, very impressive. We were seeing 4 to 5x compression on the data drives, and sometimes up to 70x compression on the right-ahead wall, the wall drive. And the storage compression isn't what we were going for, but because it's on EBS, having that compressed over the network from wherever EBS is to the instance, the performance increases that we're seeing were very, very incredible. Unfortunately, this is the misadventure slide. It didn't go well. There was, sometimes we started seeing in the kernel ZFS trying to allocate memory, and it would lock the entire machine up for sometimes minutes. And that was not acceptable. And so we went back and rolled that out. I'm keeping a little bit of an eye on those bug reports to see if maybe they get fixed. We can go back to using ZFS because it was, aside from locking the machine up for minutes, it was good. But it's a bit of a downside. Thank you very much. Happy to answer some questions. I also have a couple other people from the company. Is Craig here? So happy to answer questions. And then we also have a booth at 2020 if you want to come down anytime. We have some socks. We also have some socks here if you're interested. But thank you very much.